Hi, good evening, everybody. This is Bill Fitzgerald. I'm the Vice President of Growth and Ecosystems for SandboxAQ, coming to you live from Sandbox Studios in Davos. Very excited to have Cyriac, founder of Earli, talking about how the advances of AI in drug development. Cyriac?
Great to be here. I'm Cyriac Roeding. I'm the CEO and co-founder of Earli. We're based in Redwood City, California.
So Cyriac, you just shared with me a little bit about your company. Can you share for everybody at home what you're doing and the path in which you're taking to cure cancer?
Yeah, Earli is a bio-AI firm that is producing genetic switches. And these genetic switches are injected into the body intravenously. They disperse everywhere. They enter cells randomly, healthy cells and cancer cells if there are any. But only in cancer cells, they switch on like a light switch. And when they turn on, they genetically reprogram the cancer cell to produce its own medicine against itself. In other words, it tells it to make a protein. That protein gets constructed by the cancer cell based on the DNA sequence that we include in our own construct that is in the cell. And that DNA gets transcribed and then translated into a protein that gets expressed into the tumor microenvironment. This protein can be any immune messenger. It can be a T-cell engager. It can be a cytokine, or it can be an agonist. It can even be a combination of several. Think of it as a smoke signal that comes from the cancer and alerts the immune system that there is a problem. The immune system now gets activated, attacks, and kills the cancer.
So Cyriac, what you just described, we're operating in an environment where it takes 10 years and $1 billion to develop a drug. How long has your company been around?
The company has been around for 8 years now.
For 8 years, and you have effectively harnessed an understanding of the immune system to use it in a way for the body to absorb a medicine and then turn around and target a cancer cell. So you've accomplished target, absorptions, toxicology. How did you do all of that in that short of a time?
So first of all, it almost failed several times. This was extraordinarily difficult because we're trying to solve problems that have been unsolved for the last 50 years. Let me start by saying, what's the biggest problem in cancer treatment? What's the holy grail? Yeah. If you wanted to say it in simple words, it would probably be something like, kill the bad cells, but don't kill the good cells while you're doing it.
Yeah.
That simple statement belies how difficult this is behind it.
It's the long-term side effects of cancer that are often far beyond any sort of potential cure.
In order to do this, you kind of have to understand what's the good cell and what's the bad cell.
Yeah.
The problem is that these are not intruders, these cancer cells. They don't come from the outside. They are from the inside. They're your own cells that have mutated. So they look very similar to yours. So a brilliant scientist at Stanford, his name was Sam Gambier, he came along and he said, you know what? What if we designed a genetic construct, like a switch, a genetic switch that you could inject, and it goes everywhere in your body, randomly enters healthy and cancer cells if there are any, but it only turns on in cancer. Now, once it turns on, it then takes over the cancer cell and tells it what to do. And that cancer cell now has to make a protein, gets expressed into the tumor microenvironment. That protein can be a T-cell engager, a cytokine, an agonist, whatever you want. And it can also be even combined and have multiple attacks. Activates the immune system like a smoke signal, and the immune system starts attacking and killing the cancer. That's the concept. Now, here's the problem. There are multiple problems with this that have to be overcome in order to achieve it. The first problem is you have to even get to the cancer cell. If you want to transport any DNA switch, it has to somehow be injected and not be flushed out within minutes by your liver. The liver in your body is designed to flush out everything that doesn't belong there, from lipid nanoparticles to alcohol. So if you want to treat any cancer but liver cancer, you have a problem. It took us 5 years to solve that problem. we designed a stealthy lipid nanoparticle, which is chemistry at its best. We're using a core lipid, and then you use formulations to hide it from the immune system, to stealthify it, so that it can keep floating in your blood system and not get flushed out immediately, so that it can reach a tumor, let's say in the lung. That's problem number one. Second problem, once you're getting into the cancer cell, let's say we've made it, you're not done yet. You need to get into the nucleus of the cancer cell. The nucleus is 1/50th the size of the cancer cell, and the pores on the nucleus are 100th of the size of the nucleus. That means your package has to be exceptionally small and still powerful. That leads us to the third problem. Now you're inside the nucleus and you want to sense what the dysregulation is that causes the cancer. Well, if you look at lung cancer alone, there are over 100 different driver mutations that can cause that disease. So in other words, if you want to interrogate every single driver mutation, every single genetic mutation, your construct gets bigger and bigger and bigger, and you can't get it into the nucleus anymore. So either you are very accurate, but you can't get in, or you can get in, but you're no longer accurate. That's the next wall we hit.
Got it.
How do we solve that one? The answer laid in asking the right question.
Yep.
The question was not which driver mutation are we looking at. The question was which things are different in cancer in a nucleus compared to a healthy cell or a benign lesion.
And how did you run that level of testing?
So, and that's where AI comes into play and machine learning.
Yeah.
So what we then said is we're going to use a massive amount of data to find it. So we looked at 20,000 fully sequenced cancer samples and looked at the entire genomic data and the expression data. And each of these has multiple cells, so there's a lot of data to be looked at. It was so much data that we had to rent 4 of the largest CPUs instances from AWS for an entire month to get through the data a single time.
Yeah.
That gave us a long list of things to look at.
Yeah.
And then we made a call, a very important call. We said, we're not going to look at any driver mutations upstream. We're going to look at the downstream commonalities of any upstream dysregulations. In other words, the symptoms, called the hallmarks of cancer, such as rapid cell proliferation, lack of cell death, the classic things that define cancer.
Yep.
And then we found dysregulated master transcription factor binding sites. So now we fast forward, we did a lot of machine learning, we did massive amounts of data, and then we needed to bring it to the wet lab because we have to build a lab in the loop. We can't just say the AI says we should use this and then it's going to work. That's not how biology works.
So you validated within the lab.
We have to validate it in the lab.
in.
Problem here,
Yeah.
normally you can look at about 50 sequences a week to test them in the lab.
Yeah.
Well, we had to look at several million.
Yeah.
So we would be there in 50 years.
Right.
So we brought on an expert. We found her in Texas, the University of Texas. We brought her in. She built a massively parallel reporter assay that allowed us to genetically barcode each sequence and put 250,000 into the same batch, testing them at the same time.
Amazing. Again, high throughput screening in a
wet lab.
Yes, amazing.
The best sequences that came out of that go into our mice. Yeah. We have our own vivarium. Inside the vivarium, we test the best ones. That's how we're building our system.
So you are truly realizing the benefits and the aspirational benefits of AI in drug discovery.
That's right.
You are screening more compounds, more molecules, more assays. You are learning in the loop from each one of those. And you're condensing the time as a result of that.
And guess what we do after that?
What's that?
We instruct the cell to make a protein.
Yeah, amazing.
So now we can build any protein we want. Not quite any, because of course the cell there's limits to it, but quite unusually, we can have more than one payload coming out at the same time. One cancer cell can make up to 4 proteins, which allows us to address different pathways of cancer. Not only the immediate shooting at the cancer to kill it with T effector cell activation, but also teaching the immune system to remember when it sees a cancer cell for the future in case it comes back, to avoid recurrence, which are T memory cells. And we can make T cell engagers, we can make cytokines, we can make agonists, we can combine them. That means we're also doing protein design.
Right.
So that is also an interesting application for AI, and it's of course how the whole thing started with biology and AI, right?
Yes, yes.
But we're now basically leading the edge on DNA design using AI.
Yeah.
We're using machine learning to do identification of cancer, AI to design DNA constructs, and we can probably also use AI going forward more than we have already for the chemistry design of the lipid nanoparticle formulations, and of course for the protein design. It all comes together at Earli.
Get the full suite of AI-based drug discovery modalities. Unbelievable. I mean, we sit here, humbled by those that are out there on the front lines curing cancer. It's an amazing opportunity. I thank you for the work that you're doing, and I thank you for getting us in touch here at Davos and this wonderful forum that puts thought leaders like yourself in our path. So thank you very much.
You are also changing the future at Sandbox. At Earli, we've got 35 great souls, including my co-founder, David Sui, who's actually the brain behind the science of it. And I am excited to be here in Davos because you are seeing that there is a tremendous need and understanding for that the real applications of AI that matter in the future, it's not just the foundational models. What are they being used for?
Yeah.
How can we use AI to change biology?
Yeah.
And actually help people live longer?
Yeah.
That's the ultimate goal.
Absolutely. We're in it together. Awesome, man. Well done. That was great.